Moving on, I would like to re-invite Dr. Sudhin Tayal and invite Pete Lally and Dr. Naveen Jain to discuss strategies to ensure intact survival of neonates, including use of neurobiomarkers, MR technology and neurodevelopmental follow-up. Pete Lally is a clinical scientist and head of MR physics at Center for Perinatal Neuroscience at Imperial College, London. His research is focused on development of novel neonatal MR spectroscopy and DTI techniques for accurate quantification of neonatal brain injury and prognostication of long-term outcomes. Welcome, Pete Lally. Dr. Naveen Jain is a professor of neonatology at Kerala Institute of Neonatology, Trivandrum. He is also the co-primary investigator of multi-center study Perinatal Risk Stratification of Preterm Neonates and Developmental Outcomes. He has also conceptualized the Blue Book, which is a checklist model for follow-up, and he is also the co-editor of a book of high-risk newborn.
Good afternoon again. I'm just going to give a brief introduction to Pete's talk, and then I'll just hand over to him. So when we were designing the Helix trial a few years back, we were wondering what neurodevelopmental outcome assessment tool we should use. So the options were either to use DASI, which is widely used in India, or go for Bailey or Crickets. So when we then had a meeting of some of the key players who were doing a lot of neurodevelopment work in India. So what transpired was that DASI was developed based on Bailey 1 in I think it's 89 by Arun Pathak, which has not been subsequently updated, and then Bailey has then moved on to Bailey 2, and now we've got Bailey 3. And the concern was, A, because it is a multi-center trial, we could use only in India. Using DASI, we can use that only in India. And B, if we use Bailey 3 in Indian setting, there was a concern whether we are going to create artificial mental retardation, because we thought babies would score low on Bailey because it's designed for the UK and US population. But then when we did our initial studies in Calicut using Bailey 3, it was a surprise to us because most of the controlled children at 3 years performed above the UK norms, particularly in the cognitive area. So it is quite reassuring that we can at least use the same tool in these settings. But having said that, to use a outcome assessment tool, you need to wait at least 18 months, if not more. Often, especially if you're evaluating a therapy, you need to do a childhood outcome. So you're talking about 5-6 years. So the total duration of the trial becomes almost like 10 years. But if we use a biomarker, which is really validated, a robust MR biomarker, you can really shorten duration of the period before you get an inclination about the treatment effect. For example, you can do these biomarkers during newborn period itself, which will give you an idea of the brain injury and what the future outcomes are likely to be. Again, one of the other advantages you would then have is that your outcome is not affected by all the confounding factors which may occur after treatment is given. For example, you give cooling during newborn period, and then you wait another 18 months or 3 or 4 years before you do the outcome. And during which period, a lot of other factors come into play: intercurrent infections, socioeconomic status. So using MR biomarkers, you are actually bypassing all that. So net effect, you can do trials using much smaller sample sizes if you use MR biomarkers. So if you're doing a clinical trial using a neurodevelopmental outcome as an outcome measure, you need trials into thousands of babies. But with MR biomarkers, you can do trials with very small sizes, sample sizes. So 50 to 100 babies are a good number. So that's what Pete is going to talk about. And thank you.
Good afternoon, everybody. Thank you very much for inviting me here to talk a little bit about neonatal MRI. I'm a physicist based at Imperial College. And first of all, I'll begin with some practical aspects to getting a successful MR exam, some of the clinical benefits of MR biomarkers, and actually going on to some of the research benefits as well. So the first step is actually getting the baby. Probably the most important step is getting the baby ready for MRI. It's really important to have them settled and ready for it well in advance, because quite often you'll find that a baby might wake up partway through an exam, at which point it's impossible to get any usable data afterwards. So all the time spent in preparation, careful preparation, really pays off to getting a good exam. Exactly. So, I mean, there's no point really getting a baby who's unsettled into an MRI scan because it will be a disaster. So this is what we do at the neonatal unit at Queen Charlotte's. First of all, do a safety check on the unit, so we'll cover things like if there are any needles, any clips, anything that might be attached to the baby that could be transported towards MRI. So well in advance of going to the unit, we'll do a check for all of those things that might be unsafe. Change into some metal-free clothing for all of our babies and give them nappy change so they're comfortable. And then about an hour before the scan, we'll give them a feed so they're not hungry during the MRI scan. And when we're using sedation, we'll give that about 30 minutes before. Now that's an ideal time to think about applying some hearing protection. Now, MRI scanners can get up to 100 decibels, and not only is it going to wake the baby, but it could cause some hearing damage as well. So we suggest that people use quite a lot of hearing protection. We typically use 2 layers of hearing protection. We have some dental putty that molds to the inside of the ear and solidifies so it doesn't get stuck. And we have these mini muffs which are available. And these reduce the noise quite considerably, I mean, typically around 30% or so, and babies seem to tolerate it quite well. The other thing which is really, really helpful for us is this vacuum mattress. It's just essentially a beanbag with a pump, and you deflate it when you get to MRI, and that cradles the baby during the exam, and it actually really helps successful MRI exams. Because this is exactly what we want to avoid. If we have motion, these images are really difficult to interpret, and so you don't get any useful information. So really, the reason why we want to go through all this pain to get the babies so prepared for the MRI is because it's such an incredibly powerful tool for looking at all different types of injury. And it's also been behind some of the groundbreaking discoveries especially in neonatal care. So the initial work on cooling was done using MR biomarkers. And also in the clinic, it's a really useful tool to be able to look at long-term neurodevelopment straight away to give a good indication of how these babies are going to do. And for also, as Susan mentioned, powering these clinical trials, so we need fewer babies and less time to transition these therapies into clinical practice. So we'll start off talking about the revolution of cooling in the UK, how MR biomarkers were behind that. So in 1995, groups were looking at the use of phosphorus spectroscopy using MRI scanners. Now that's not widely available in a clinical setting, but nonetheless it gives you a non-invasive way of measuring energy metabolism in the brain. So what we're looking at in HIE is impairments of this normal generation of ATP, a buildup of phosphocreatine, and a breakdown of phosphocreatine and a rise in inorganic phosphate. So we can measure that with MRI non-invasively, and we can come up with a preclinical model of HIE. So what they saw in 1995, this was long before it reached clinical practice, in piglets, if they induce hypoxic ischemic event, this ratio decreases down during the insult. It rises back to normal, but if these babies aren't cooled, if these piglets aren't cooled, their energy metabolism reaches something called secondary energy failure. However, with the introduction of cooling, you can maintain similar conditions as the healthy controls. So this was clear evidence that cooling is doing some kind of neuroprotection there. And at that stage, it still took 15 years for it to be considered a potential clinical tool in the UK. So in the clinic, what do we have available? We've been doing this for a long time, so after looking at all the different patterns of injury on conventional imaging, we've got quite used to looking at those images and predicting our outcomes. And this is what you typically get in an MRI. You get a T1 weighted image and a T2 weighted image. So say for example, you might look at the internal capsule here and you can see myelin is quite bright, which is with short T1, and you can see that quite clearly. So that's a good indication of how well the baby is developing. And if there's been any injury to the deep grey matter or the white matter, it can be picked up quite well. And in fact, it's the injury to the basal ganglia and thalamus which is the most predictive of adverse neurodevelopment. This is one of the scoring systems you can use to make it more of a semi-quantitative tool. This is a guideline presented by Mary Rutherford, which shows just how the appearance of the basal ganglia and thalami are in different grades. So this is mild injury going on to more severe injury, where you can see a lot of heterogeneity in high signal there on the T1 weighted image. And also on the T2 weighted image, you can see different grades of white matter injury. So going from a normal brain through to more and more abnormal white matter signal there. Now it can be one of these in isolation, or it can be a combination of both. The other thing that we can use to add to that picture is diffusion weighted MRI. So this is what we call an ADC map, which essentially maps how far water travels in each part of the brain. If you look at the CSF here, there's no microstructural barrier, so it diffuses quite well, so the signal's bright. In a deep grey nuclei and in the white matter, it's less free to diffuse. So this is another more quantitative technique of using MRI. For a particular scanner, you can look at the typical normal ranges you might see in your babies. So to take you on to a case that we had at our unit, this is a baby who was presented with HIE and was scanned at day 4 after rewarming. And if you look at these images and then compare them to the scoring system, I'm no radiologist, but I'm sure you agree that you wouldn't expect what we saw when this baby came back for an MRI later on. We were lucky because this baby was enrolled in part of our research, so we were able to get a second scan at 30 days of age. So our usual window for MRI is 4 to 14 days, but this is what we saw at 30 days, and it's quite a catastrophic injury. And so this really indicates that imaging isn't the only way to go. There has to be more to this. So to summarise about conventional imaging, it's subjective, it's only semi-quantitative, and I'm sure you'll agree it's very difficult to find somebody who has this kind of expertise. It's such a niche subject. It doesn't always give you an idea of what's going on in the tissue itself, and so it's really difficult to say if there's a change in the T1 weighted image, what's actually going to the brain. So this is where spectroscopy comes in, and this is where I'm quite passionate about the use of spectroscopy. It's another non-invasive way of looking at the brain metabolism, and it's available on every single clinical MRI scanner, but it's vastly underused, and it's got clear benefits in neonatal encephalopathy. So we're looking at 4 primary peaks in HIE. We're looking at anastyl aspartate, which is this peak here. It's primarily found in the neurons, and it's considered a surrogate marker of neuronal integrity. There is lactate, which is a product of anaerobic glycolysis. Choline, which is a composite peak, which indicates memory turnover and synthesis. And creatine, which is related to energy metabolism. So this is what you might consider a typical HIE spectrum. And this is where we look at the signal. So when we're doing spectroscopy, we'll choose a small area of interest, and typically we'll choose the thalamus because that's so metabolically active. So here we go. Here's one case who's likely to have a good outcome. There's a high NAA peak and a very low lactate peak. As the injury is more severe, you'll see a reduction in this NAA peak as the neuronal integrity is impaired, and the lactate peak will increase just because of the anaerobic conditions. Now back to our baby at day 4. Had we looked at the spectroscopy at the same time, we would have seen this large lactate peak here, suggesting really quite profound injury that's going on. And it suggests just how important spectroscopy can be in these ambiguous situations. And in fact, our group did a meta-analysis in 2010 which looked at these different biomarkers. So these are both derived from spectroscopy. This is derived from conventional MRI. The PLIC is the grading of the high signal that we see in the myelin in the internal capsule that I showed you previously. And the ADC is the diffusion. And quite clearly, the spectroscopy biomarker of lactate to NAA is the most predictive of adverse neurodevelopment. So these were compared with neurodevelopmental outcomes in the various trials. And this is the motivation for the MARBLE study. So this is a UK-based study with a few other centres in a couple of countries. And we were looking at the use of these biomarkers in a very controlled setting. So So I'd go to all these different sites, help set up the protocols, and see if we could really compare these different biomarkers, see how they predict outcomes, and compare them to neurodevelopmental outcomes at 2 or 3 years. And in fact, in the first 54 babies that have come back for 1 year follow-up, we've looked at lactate to NAA in those babies, and you can see a huge sensitivity and specificity for identifying those who will go on to have adverse neurodevelopmental outcomes. So in fact, if you choose the right cutoff, you get 100% sensitivity and 91% specificity. There are only 9 cases who came back with an adverse outcome, but it's really promising. And so really, that's one of the motivators for using it in Helix as well. We know that it's so highly useful in predicting neurodevelopment. So I'm sure you've already heard about the design of the study. We will be applying all these M1 biomarkers again in the population here. And for example, here's some of the some imaging that was done in Chennai on a 3 Tesla scanner there with a spectrum which is much nicer than anything we can get on our Queen Charlotte scanner. You can see that the deep nuclei look quite normal here, but there is some highlighting of the cortical grey matter and white matter. Now, this suggests something maybe more like a stroke, but you can see spectroscopy has borne that out. It doesn't look like HI, grey matter seen intact. So based on that perspective, they're more likely to have a good outcome. And here's another set of data acquired here. This is more typical of HI. You can see the focal lesions here in the deep nuclei. There's no signal really from the internal capsule. You can't see too much myelin there. And this heterogeneity in the deep nuclei in the T2 weighted image. And you can see there's a reduction in this NAA peak and an increase in this lactate peak. So that's typical of HI. But there's an important rider to this. We had a case that was sent to our centre for cooling, and we're very lucky in our department because we have an MRI scanner inside the neonatal unit. So we were able to do an MRI scan during cooling on day 1 for this baby. And despite the spectroscopy showing that there's a huge lactate increase, suggesting HIE, if you look very carefully, there's a huge lesion in the spine here. So it was most likely that the vast majority of the symptoms that this baby came with were related to this lesion here. And there might be some degree of encephalopathy on the top, but this is something that's really important to watch out for. So spectroscopy isn't the answer. It's part of a wide variety of tools that MR can help with. And just to go on to where we can translate this into research studies as well. So looking back at diffusion, just to describe what we look at when we're looking at diffusion tensor imaging. So this is a more advanced diffusion technique which uses the properties of different tissues to identify them based on the diffusion. So if you look at this electromicrograph of an axon, water is much more likely to diffuse along the length of the axon than across it. So you can see that the diffusion is quite anisotropic. So if you imagine that's the direction of your axon, water is much more likely to diffuse freely along here and less along here. Whereas in the CSF, there's much less microstructural barriers, so water diffuses quite freely. So we can use these different properties of the water diffusion to distinguish between, say, for example, white matter and CSF. And one succinct way of describing that is the fractional anisotropy. So white matter we expect to be highly anisotropic, CSF less so. And what we can derive is these maps of fractional anisotropy across the whole brain. So we can pick out quite clearly these white matter tracks around here. As we go through the axial slices, you can see the internal capsule, corpus callosum here. And a change in this fractional anisotropy has been linked to a poorer outcome or a more severe encephalopathy. And one thing that's really useful about this fractional anisotropy map, you won't get anybody analysing this on a case-by-case basis and saying, oh, the fractional anisotropy looks strange. But what you can do is you can buy this data across a lot of different subjects in a really powerful way. So say we've got a few different subjects here, you can get all of these maps and combine them together and do group-wise analysis. So here is a kind of mean of all those white matter tracks. Those regions in green are where we'd like to compare a group A with a group B. So for example, cooling versus non-cooling. If there is a significant difference in some of these white matter tracks, they'll light up as red or yellow depending on the significance. And this has been shown, it's been validated in different groups. So there is a reduction in FA with poorer outcomes in encephalopathy, but with cooling, this is protective. In the same way, those with more severe injury have worse FA values. So this is some data that was acquired back in 2009 in Calicut of 54 babies who were able to have diffusion tensor imaging. And we could see that actually there's some profound differences in this white matter microstructure, and that's related to the severity of encephalopathy. Now, what we can also do with more advanced diffusing models is to relate that to the actual, what's happening at an actual tissue level. So this reduction in FA doesn't mean a lot to anybody, but if you relate it to the properties of the axons themselves, you can see that this suggests that there's a decrease in the axonal density in these white matter tracks, which has a big clinical significance. But it's answering a very important research question as well. So this is where MR biomarkers can also be very important for looking at characterizing brain injury when they might not be necessarily useful on a case-by-case clinical basis. So to summarize about MR biomarkers in this talk, they fall into two main categories. There's the clinical benefits of MR biomarkers, and there's the research benefits. So really, the key benefit that you will probably see from MR biomarkers is that, say, you can do a scan between 4 and 14 days, and quite early on you can say to parents and you can say to your colleagues, this baby is likely to have a good outcome, this baby is likely to have a poor outcome, and plan accordingly. And that's one thing that spectroscopy has a huge potential role in. But also in research for applications such as the HELIX trial, we're able to use these validated biomarkers to really reduce the number of babies we need to put through these clinical trials to get therapies into clinical practice. So really, these will contribute together to give some real benefits for both. If we're able to get more therapies tested through clinical trials with more powerful outcome measures, then we can get more therapies into routine clinical practice. Thank you very much.
Fractional anisotropy and MTR sequences. So if that is there, I'll just add that before I continue on to the discussion part. I think it will be appropriate to pay respects to my mentor and teacher, Dr. M.K. Sinaya, who got me interested into neurodevelopment, and I'm formally not trained in either of any of these tests or follow-up. And whatever interest came in because he kept giving me work and I tried doing whatever work he gave me and slowly got interested in the subject completely. As we started doing some follow-up, we realized some changes that had happened from what we were seeing in 2000 in PGI as residents and from what we started seeing now as probably 15 years down the line. At that time, I don't know whether we were doing the right things or wrong, but we used to play around with the ultrasound machine in the NICU. We would do scans on the first day, third day, seventh day, and we used to pick up what I thought at that time was intracranial hemorrhages or intraventricular hemorrhages. And as we started following up, we realized that these so-called hemorrhages had started getting away. We were not seeing many of them in our, but still babies were having developmental problems. And the curiosity and interest went on and we started trying to learn something. And before I go on to the part which really is sharing experience in trying to get interaction from all of you, is just this part of new science and adding on to what Dr. Pete was trying to tell us. There's a whole new word we have moved on to called dysmaturity of brain development. It's no more injury. We are not talking about just a preterm baby who has got an ischemia, an infection, and his oligodendrocytes have been killed, and there is a white matter injury, and then we went on to say this is not white matter alone, this is grey matter also goes away. So we started talking about cortical volumes being measured. We moved one step further and we said there are babies who don't look abnormal on the scan, but still have developmental problems which are not just cerebral palsies, the cognitive problems, behavioral problems. So there has to be some basis behind it, some biochemical basis behind it. And then these kind of scans which you showed us just now started developing interest. So this is the basis of your brain. So this part I understood easily, so I picked up this slide to show all of you. Is basically we're talking about an axon and the myelin around it. So if there is some way I can study this basic structure of the brain and its function, I would know that I'm going right or wrong. And when they started looking at what can study the axon structure, it is your fraction anisotropy. Actually, I understood better when you showed me on the slides what is anisotropic about it, but just to understand that, you should have a fraction anisotropy to understand whether axon development has happened properly or not. So when they looked at preterm babies' images at 40 weeks at estimated term age, who were otherwise normal and not having any evident brain injury, there were large areas of the brain matter which were falling far behind the development of a term baby at that age. Their fraction anisotropy said that this baby has not caught up. There is a dysmaturity. Now this might seem quite logical. Now if we did not produce hypotension, we didn't produce asphyxia, we did not produce infections, we didn't produce hypocardia, then why is this baby not there? And then we start learning a lot of other things we discussed today, the nutrition. We went on a further step, placental hormones, what are required. Estrogen, progesterone levels are 1,000 times or 100 times more before the fetus was born. And this baby is delivered suddenly and they are all gone. They have a huge role in development of alveolar cells, brain cells. But this need to understand these things have started coming from moving beyond injury. We are not now talking about an injured brain. Unless we talk about that, we are not going to look at an intact baby at the end of the day. So, this is what I was trying to tell you. This is simplistic language I could understand by trying and reading more and more literature. That one way of knowing axon maturation was looking at the fraction anisotropy. Some other sequences can look at the myelin development, and these are some of the images which I picked up. If there is something you can correct, you can please tell me. Okay. So they were showing that the areas which are blue in a preterm baby who became estimated term age, this is one where he fell short of development in the axonal development even at 40 weeks, even though there was no evident injury. And similarly, myelination could be done, and other functional images could be done where you could study the metabolism of the brain and understand that a preterm baby is not doing the same job as a term baby would have been doing at that age. So something is falling short. Now having said that, I will try and stay away from what is not my area, close the slides and then go on and share some of our personal learning experiences and ask you to contribute in some way, and we can go on from there. The first one is why follow-up studies don't happen. Why follow-ups don't happen. So Sudhin was there this morning, we were having breakfast together and we said Kerala is unique, we get 85% follow-up, whereas in other places of the country only 40-30% babies come back. So why is that they don't come back? I will share a story which we had learned, and what is the role of health education in trying to get these things happen. One of the observers, Dr. Moli, who is now working in North Kerala, came to us for a short while for training, and she asked me on the rounds, this baby had an ROP screen last week. Why is that we are again subjecting this baby to another ROP screen and you're scheduling one for the week after? While she was just telling me this, the mother who was standing behind said, doctor, this is because we want to see whether the blood vessels are growing normally and whether they have grown to where they should grow. This is because she had a health education session taken by a non-medical, non-nurse, non-developmental specialist. Those who did not and missed the session by chance came to me and said, do you have other ophthalmologists in your hospital? I said, why is that? What is wrong with this guy? Last week he dilated the baby's eyes for 4 hours, looked into the eye, baby was crying, and now he wants to do this all over again this week and next week. So unless you educate the family while they're in the ICU, while this process is happening, you're not going to get them for follow-up. They have to come back. Incentives can't bring them back. Now, the lack of education happening at the right time can be dangerous. If you start talking to them for the first time about retinopathy of prematurity, when the baby has recovered and is ready to go home, at least in Kerala, I was telling him, that they will be sure that you did something wrong and you don't want to tell them now. That is why ROPS happened. But if you had put this leaflet and introduction on the second and third day when the baby had started recovering, that you're going to have sessions about ROP coming, babies having a premature retina, they will need checkup. This is not the time, I can't talk to you all about it just now. This will happen later. So we have tried to move a second step from here. We haven't done it fully to develop small modular videos, because that will prevent that the messages which are repeated over the time don't lose their impact or don't become different. But unless we educate the family from the first day why follow-up is necessary, it's not going to happen. So that is the first thing I want to share. If there's somebody who wants to add on to this part before, how much time I have? About 10 minutes? Yeah. I have about 6-7 points that I would like to share what we learned in follow-up process. Anybody wants to add, madam?
Same thing, importance of spending more time for counseling.
Yeah.
That helps.
Yeah. The second one I would like to bring about is what we learned is curiosity of initial developmental assessment was just to know whether this baby will become okay or not. So in the first year when we started doing transports in Trivandrum, we just wanted to know all the sick babies we are bringing back, are they okay or not. So that is why most of us want to do development really, at least in the beginning, to do follow-up assessment. But then we figured that this is not the only important thing that we achieved. And my colleague who is sitting here, Dr. Adhikar, did our first study on follow-up structure. We followed up for 5 years and we said the known perinatal risk factors, let us say antenatal steroid given or not, asphyxia yes or no, what is the gestation, birth weight, these are well described in literature. But let us just rank them as maybe mild, moderate, severe and say you had hypoglycemia, yes, no. You had jaundice, more than 15 milligrams in a preterm baby, yes, no. Because at the end of the day, I can't tell the family that you are going to be good because you had no hypoglycemia, bad because you had meningitis. At the end you have to have one outcome. So then we try to rank these and then we try to do single univariate associations between these risk factors and outcomes and then try to see whether you could develop a model. So what we landed up in a small cohort of 250 babies, that we found that if there was a score of say 2, which meant one risk factor, the risk of developmental problem was only 4%. This is the baseline risk in BLBW babies. But if the risk factors went to 2, a score of 4, the risk went up, and when it crossed 3 risk factors, maybe something like 60-70% babies had a problem. So, but these babies were only 12% of the whole population we were following up, which means we could channelize our resources and tell this 12%, look, mark it on the chart, these are your risk factors, you need to come back to us. And the others, not that they're free, they could follow up in a primary setup and they could mark some flag signs and then come back. And in a country like ours, getting 80% of the babies away not only reduces the load on the system which is doing follow-up, it is very tedious for somebody to go to Hubli, come back to Bangalore and find out you're doing nothing for them at all. So it is very unfair if you're not going to produce enough result by getting them back. So this predictor model was done only from one hospital. And for those who are interested, you know that you couldn't validate this result unless you tested in every other setup. As a part of this, Kerala University has funded a multi-site research which my teacher and mentor Dr. NKC is guiding. And many of us here in this hall, Kumuda Madam, Karthik sir, Arvind Shenoy's unit, many of us are participating in collecting data. And first phase is over 1,500 babies have been enrolled and who are less than 33 weeks. We're waiting for them to complete at least 1.5 years of corrected development. And another phase is happening because we learned from the mistakes of our first trial and we corrected some parameters and we're collecting data again. So hopefully in another 2 years, we may be able to tell at least 2 or 3 things. What is happening to Indian babies from across the same country, something like 25 centers are participating. And then we can compare and give some idea whether the risk factors we found are the same. How do you tell the family whether baby is at risk or not? In this process, we realized that what I wanted to do in my unit is not what my residents were doing. Initially it was anger, disturbance, but then I thought, why are they not doing it? There was no structure that was available to them. You don't miss a single vaccination. Everyone comes back, but you miss follow-up systems because there is no vaccination card. So we then developed a day-to-day basis a program. This is the thing you should do on first day. It is very simplistic, everyone can understand. What should you do on the first day? You risk the risk factors known perinatally, ask for mother's milk, On third day, you do a thyroid screen, record the first head circumference. Because otherwise, what would happen? By the time you start thinking head circumference, baby has actually recovered and ready to go home. So how do you have a serial head circumference? So this kind of a checklist model helped standardization of procedures, didn't require any brilliance or newness, but just required listing out, these are the 3 things you need to do every day. We still forget, we still miss. Our audit was only 80% compliance in spite of having this on the website. And I will just complement this information that every parent asks only for a normal baby. Every conference discusses only about intact outcome. Every research wants to end up only in finding out intact outcome. But tell me one vital sign on your chart which is talking about brain outcome. Heart rate, temperature, respiration. Where is the mention of the brain on your monitoring chart? And 13 years back, we added a column called sensorium, which was a parallel at that time what Linda de Vries presented on your sleep, on your amplitude EEG, which was not bothered about the shape. It was only just saying low voltage, high voltage. Is the EEG okay through the whole brain? And we just said, let us say that the sleep-wake cycle of a baby is 4 hours. 5th hour, if he doesn't wake up, then there's a problem. And we asked the nurses to record. This was just going to make it as simple as the level. We didn't train them on what you would record. So 5th hour, they would call and tell me the baby is not active, resident is not listening to me, there is some problem. And then we tried to look at simpler testing initially, and we found among the 75 babies we transported in the whole year, if the baby was having poor sleep-wake activity for dash period of time, this was as good a predictor as the lowest pH, the lowest blood pressure, and the condition of transport in many of the part of the SNAPI scores or whatever scores on the first day. So having this adds an entity called Think Brain. If you read the Hammersmith tool, the first page is a beautiful one which Dubowitz says, everyone talks about intact outcomes, but nobody wants to measure it. And this is because we think neurological examination is complicated, it's difficult. I am not a proponent, I have neither been trained in Hammersmith tool, we just virtually pirated it from the website and started using it. But I can tell you it is very simple to do. Anybody who reads the tool for the first time can do it, and a baby at estimated term age or asphyxiated baby should have one neurological examination. In a short of time, I'm not going to go to the depth of Hammersmith tool. So that is the second thing, have a structured follow-up model, have one neurological examination of newborn model, it could be anyone. Really, the complexity of the tool, whether it's Bailey or Screener or a Hammersmith, doesn't matter. It should be simple to do, where everyone can do. Then came the book which NKC sir wrote and asked us to contribute. I think at least 20 people in this hall have contributed some part of the chapter of that book, which was called the High Risk Newborn, where he said don't write neonatology, that you have been doing all your life. You write in the jaundice chapter what risk factors are known that can predict injuries in jaundice and what best care practices you can recommend that will reduce brain injury. Karthik sir wrote on the asphyxia chapter in that. He didn't write about management of the asphyxia, he just wrote what reduces brain injury in asphyxia. So that kind of a care practice model came, and thanks to Vikram sir, this time we landed up writing for the Journal of Neonatology a whole chapter, again where more than I think 50 authors are there from the country, where we just tried to pen down something like 56 best care practices. This is it. At least these 56 have clear evidence, starting from something like antenatal steroids, giving antibiotics in rupture of membranes, or saying that you make sure hypocarbia doesn't happen. At least this you do. Go back to your files and put this in your file and say, these 56 things I won't go wrong. This is what science knows today. I should not go wrong on these. So this is the next step I would suggest. It is available on the website free. You can download it. These are not comprehensive by any means, but even if you can pick up 50 out of 100, I think we will reach somewhere. How long to follow? I think anything short of 2 to 3 years is very, very less. This is not based on research, I am saying based on personal experiences. Babies who we clearly labeled as okay, nothing wrong, they passed their Denver test, they passed their Darcy's tests at 1 year, 1.5 years. At 2 years, the father came and told me, I don't know why my fellow walks with one hand like this all the time. And that is when I picked up that he's got a hemiplegia. Most of the language problems and schooling problems crop up later. And what I showed you on the dysmaturity of the brain, gone are the days when we're talking about skewed brain injuries where only cerebral palsy, blindness and deafness is being discussed. They're gone. They are not the problems. The problems are, for those who have seen the movie Tare Zameen Par, anybody who has not seen? Okay, everybody has seen? Okay. Okay. I'm not sure that people are there who missed it. So it's a traumatizing experience. You have to see to understand what we thought as minimal brain injury is not minimal anymore. It's very, very disturbing because if you have cerebral palsy, everyone knows and it gets attention. But if the child has a developmental problem, learning problem, it gets missed. And there, because probably we didn't do something of that maturity right. So unless we start doing these kind of scans and understanding what are we missing out? Is it that we didn't give the right protein at the right time? That's why they didn't reach the maturity? Do we need to give placental hormones to a fetus after birth? Is it glucose that is not a nutrition? Is it protein? So that understanding will happen only from these kind of scans, and then we will understand where we are going. So I think I won't take longer than that. I'll just end with that and just add one word which we think is changing the way we are practicing is please add think brain to your daily charts. Go back and put somewhere one column on your file which says, have I done everything right for intact outcome and not just survival? You will discover your own practices, your own best practices list, your own models, your own health education, your own blue books. But you cannot pass from one day to another with just doing a blood gas or getting a PCV or a bilirubin. You must be talking of, is my practice today in the best interest of this baby's outcome?
Thank you. Thank you. Any questions?
From the talk, what I understand, it depends on the area of mapping where you are doing it in the brain, right? Now, if you give an MRI scan to 10 people without an area mapped out where you have to do the MR spectroscopy, what is the inter-observer variability? Has it been assessed, and if so, what does it come out?
Okay, so a lot of my job is assessing a lot of these kind of inter-case variabilities, and generally with, say for example, looking at spectroscopy, you can expect variation of perhaps 5% on an individual from case to case. But, so is your question in terms of regional variability, or is it in terms of...
Well, what I'm asking is, you get an MRI scan,
yeah.
you want to do MRI spectroscopy for the 4 peaks. Now, you might map on area A when you're given the scan.
Sure.
It goes to another physicist who maps the area B, thinking that is the place to do it. There may not be a consistency of the marked area, because it will depend on the physicist where he's putting the square. How much is the variability then observed in the results between different observers or different physicists reading the same MRI scan?
I mean, I put that very, I mean, it's very hard to quantify in a single number, but say, if you look at maps of spectroscopy across the whole brain, particularly in primarily being done in adults, you see that the concentration of, say for example, N-acetyl aspartate is very uniformly high in the deep grey matter, and then maybe comes down by 20% or so in the white matter. But it's a similar map for all different metabolites. So depending on the regional variability, there is some regional variability. So it is important that people are well trained doing the spectroscopy to make sure it's in exactly the right place. Every time I'm analysing spectroscopy, I make sure that I verify exactly where the box has been placed, that the baby's not moved. That's an important aspect because we take images before and after just to check, because you don't actually have an image for the whole time of the spectroscopy, so a baby could easily have done that and you're looking at the completely wrong area. So it is difficult to quantify, but you can really build in some quality assurance to the analysis side to make it as confident as possible.
Add on to the curiosity which Dr. Samir was asking. We have done a study on something like 250 MRIs on babies and tried to find outcome. The difficult part is we didn't know whether reading the MRIs correctly at all. Because we either had an adult radiologist or a pediatric neurologist who had never seen 27 weekers before. So then, recently I saw an article which talks about automated MRI reading based on some principle called strobography, which moves from one pixel to another pixel and looks at a principle. Strobography is really to do with epidemiology or research methods that says that you can't move from one gradient to another abruptly, and then maps out pictures of white matter and say that this is normal because you have gradiently moved from one side to another. It is published last month, and they have actually shown MRI pictures and how you will superimpose this on that, and picks a whole image of the brain, shows a blue area that says this is the normal white myelination, and picks up some areas where pixels are abruptly moved. And probably they're looking at this as the future of a clinician reading MRIs and knowing that things are not right. So please comment on that. I don't know about it.
Sure, I mean, I'll have to read the paper because it sounds very interesting. One of the real skills in radiology is being able to identify artifacts as well, though. So if you imagine how many babies will be scanned for these studies and how many of those might have a small amount of motion, even from something like breathing, I'm sure that will probably complicate the analysis. And when you sit going through these scans of the radiologist, it's a lot of different aspects that make up the picture of HIE. And I've tried to read some images based on the criteria, and I've failed miserably. So I'd like to think that we're not putting the radiologists out of jobs, but it may well be a really useful tool to have alongside what's available, because it is very difficult to find expertise. I mean, there's very few people in the world who will have that experience looking through the neonatal MRIs and assessing them.
Because we tried doing MR spectroscopies in some of the babies for metabolic disorders. We got the whatever graph or the picture, and then my radiologist says, look, I don't know how to read it. Can you find a metabolic expert who knows what is on this image? I can show you this is the image. So I'm sure this is going to be a problem in most of the centers now.
Yeah, well, one of the key issues with MR, it's a bit like stethoscope. The most important part is between the earpieces. You can't put the baby into MR and push a few buttons and expect to get the data you want to. You really need to harmonize the sequences quite carefully. You really need to optimize how all the techniques, all the voxel positions, sequences to use. So for example, the study Pete did on Marble. So he spent almost 6 months going around to different hospitals and looking at scanners and training the radiographers to do it properly. And that's exactly what Pete is doing now in Chennai and Bangalore. Once you've done that, then you will get accurate data which can be interpreted. But if you don't do that step, you get the data out and nobody can actually interpret that. It will really affect the values.
I don't know, because this is not my area of expertise, but it may be interesting for you to look at that article which has come. A very large number of babies they have scanned, and they have done an automated picture which they are saying will be midway between application for radiologists and clinicians, and it will show you red dots on where areas are problematic.
There is quite a bit of work that is going on both in India and UCL to develop automated systems. If there is no MR visible injury, if the injury is very subtle, those things are useful. But if there is gross injury, you can never be radiolized with those automated systems.
Yeah, just a small question. I don't know if it is relevant here. In the study, you've actually used a 3 Tesla MR for the MR spectroscopy. Can you use this one which is a lesser Tesla? 1.5 for example.
Yeah, I mean, it's available on all MRI scanners. The reason why we choose 3 Tesla is because we get a lot higher signals from the brain at 3 Tesla. So the signals actually double compared to the noise. And we get much sharper peaks. So you can definitely do spectroscopy at 1.5 Tesla as well. But you just have to be prepared for a slightly lower quality of the spectrum.
Dr. Sudhir, is there a scope for, say, teleradiology services where we can send our MRs down there and
Of course, I think most radiologists, that's what they do these days. But
the other way around, actually, they send it over here.
You can send across, yeah. But having said that, we just need to think who is going to do the neonatal MR reporting eventually, or who should be doing it. In the UK, there's a medical legal issue that we have to get a radiology report. But if you look at all the leaders in the field, Francis Cohen, May Rutherford, Stuart Miller, none of them have been radiologized. These are either mostly neonatologists who became experts in that field. For cranial ultrasound, I don't know, it's usually the neonatologists who do, not the radiologists. So whether you would consider getting that expertise, and neonatologists start reading the these MR scans would be one option. But certainly, yes, sending abroad is an option, but the cost, I don't know how that, logistically that would work out.
And also the confidentiality and stuff, so that will be an issue. Okay, I think we should wind up the session. So just to summarize, as Naveen had told, so just definitely think about brain in your day-to-day practice. That's the first thing. And the second thing which we wanted to look is obviously Pete told about the surrogate markers, but the long-term neurodevelopmental outcome. There are several tests which, as Naveen told, you can use the Denver or the Baileys or the Griffiths. There are several things, but make sure you use one of them. The whole idea here is to pick up a child who is not developing well, start the intervention. I don't care which test do you want to use, but just use any test so that you can pick up the child.
We'd like to thank Dr. Naveen Jain and Pete Lally.